thank the organizers, in particular Nikolai, for inviting me here. It's a pleasure to be here. Also, I want to apologize to you, Nikolai. I think this is what you already heard to a large extent. I think I need to okay. So, as already announced, I'm going to give an approach to geometric methods in simultaneous approximation, particularly use the parametric geometry of numbers to do some simultaneous approximation. Let me start by a brief overview of what I plan to do. So, in the first section, I intend to explain to the non-experts how geometry of numbers comes into play quite naturally when dealing with questions of simultaneous approximation, and in turn introduce some new approximation constants. I should mention also that the work I'm presenting here is joint work with Wolfgang Schmidt that has evolved during the last couple of years and is still going on. In the second section, I want to use the successive minimal functions that I got from geometry of numbers to get quite a general picture of these functions that encode most of the properties of simultaneous approximation for the given numbers to approximate. And finally, in the third section, move on to some concrete problems of approximation in dimension 4. On the one hand, simultaneous approximation, on the other hand, simultaneous approximation to linear. There's a motivation. I was told any good talk in simultaneous approximation should start with Dirichlet's theorem, so here it is. And, well, we use the parameter form, and it asserts that given real numbers and the parameter q larger than 1, there exists always an n-tuple of integer points satisfying those inequalities. And asking ourselves, what does that mean from the point of view of geometry of numbers? Well, you define a suitable lattice, depending on those points that you want to approximate simultaneously. And you define a certain convex body or a relative magnitude fact that depends on the parameter q in the theorem, given by those inequalities. You compute the determinant of the lattice. Turns out to be 1, as you easily check when you look at the determinant of those linear forms involved. And you also compute the volume of the convex body K. Does not depend on Q, and it's 2 to the n, where n is the dimension, and hence Minkowski's theorem tells you that K of Q has to contain a non-zero lattice point, and so you're done with also, Minkowski has introduced a very important notion relative to geometry of numbers, which is the successive minima with respect to a lattice and to a convex body. He defines lambda I to be the infimum over all lambda, such the blow up of the convex body by a factor lambda contains linearly independent lattice points. In our case here, as the convex body depended on a parameter q, we will have functions of this parameter that we have to study. Just for convenience, switch the parameter, capital Q to e to the n minus 1 q, and the minimum function lambda I of q. So these functions that we're going to study completely, but they're logarithm. And so the L sub I, the logarithm of lambda I of q, is the functions that we're going to be interested in for the remainder of the talk. Why are these functions L sub I? Well, they have some nice properties. In particularly, they turn out to be continuous piecewise linear functions of only 2 slopes, namely minus n minus 1 and 1. When you investigate them further, you can also see that the sum of these functions is also bounded by a constant that depends on n only. This stems from Minkowski's second theorem. So you have the product of the minima is in between two constants that depend on n only. When you pass to the logarithm, then you get something about the sum of the L sub I, and this is exactly what is written down there. And finally, another important thing is that when the real numbers that you intend to approximate together with 1 are linearly independent, you have the nice property that for two successive indices like I and I plus 1, the functions L sub I and L sub I plus 1 do always have points common for arbitrarily large q. L sub I is equal to L sub I plus 1 for a certain arbitrarily large q. Now we'll refer to this just by saying the lattice lambda of psi is a proper lattice. So now, approximation constants. There are already several approximation constants, but we defined some new constants because they were suitable for our work in the following manner. So you consider the quotient of L sub I divided by q, which is quite natural since they are linear, piecewise linear functions. And when you divide by q, you're sure that the following two limits make sense. So we define phi sub I overlined by the lim sup of this quotient as q tends to infinity, and phi sub I underlined by the lim inf of this quotient as q tends to infinity. Let us immediately check some quite easy properties. We have phi sub 1 less than phi sub 2 and phi sub 3 either overlined or underlined, of course. They are bounded by minus n minus 1 from below and 1 from above, simply because of the functions L sub I have slopes only 1 and negative n minus 1. So it's easy. From the definition of the lim sup and the lim inf, it follows that phi sub I underlined is less than phi sub I overlined all the time. One can give more precise bounds for these approximation constants as well, but we will need them later, so I just mention it. And the fact that lambda is proper will imply that phi sub I plus 1 underlined is always less than phi sub I over. It's just a transcription of the fact that L sub I plus 1 is equal to L sub I for arbitrarily large, for certain arbitrarily large q. Okay, so far for the approximation constant. Of course, we have already some well-known approximation constants that are defined in the following way. Let's start with omega. Omega of I was defined as to be the supremum of omega, such as the system, which is quite similar to Dirichley's system we had in Dirichley's theorem, except for we replace the negative 1 divided by n minus 1 by minus eta now, and look for the supremum of omega, such that this has bilinearly independent solutions for certain arbitrarily large q. For omega. Now, if we ask for this to have a solution for every sufficiently large q, then it's the omega hat, which is defined by this. Okay? And what now is the connection between phi and these constants? You have a close connection between omega of I and phi sub I underlined, and between omega hat and phi sub I overlined, which is given as follows. Which means that any inequality between omega and omega hat can be transcribed in an inequality between the phi. And if I write omega without an I would always mean omega of 1 for omega star, it should be always be omega star of 1, so I equals 1 case. This point also I want to mention that I did everything so far for simultaneous approximation, but the dual problem, approximation of a linear form, can be treated in exactly the same way. You get similar constants, phi sub I star and phi sub I underline star and phi sub I overline star, but you can reduce those to the phi sub I by Mahler's theorem, which which tells you that for a lattice you have lambda sub I times lambda sub n plus 1 minus I star is of order 1. And hence you get a relation that is dual to this relation here for the omega star and omega hat star, which I don't have on transparency, but I can write it down very quickly. 1 plus omega star of I times 1 minus phi sub n plus 1 minus I over line is equal to 1 plus omega star hat of I times 1 minus phi sub n plus 1 minus I underline. It's simply because this implies, of course, that phi sub I underline, for example, is equal to negative phi sub n plus 1 minus I. This is the other way. Start here and we'll start here. If you use this, okay, so duality also comes into play. Let's see now what we can do with those approximation constants. Well, first of all, we have some well-known relations between these approximation constants, and we may rephrase them in terms of phi, which shows you here, for example, Khinchin's inequalities, that they have a very, very easy to remember form. Because phi sub 1 underlined is the least of the approximation constant, and it's always negative or 0. Phi sub n overlined is always positive, it's the largest one, or 0. So if you take once the negative one is n minus 1 times the positive one, it's always greater or equal to 0, which is easy to remember. And on the other hand, if you interchange the coefficients 1 and n minus 1, you get something that is less than or equal to 0. So in this way, easy to remember the Khinchin inequalities. Another example, Yarnik's identity. It's a special feature for case n equals 3. And also you get a quite easy formula using the phi sub I under a double line. Now, before I go to the next slide, remember the Khinchin's inequalities again. So we have this expression estimated by 0. And this other expression is also estimated by 0, one on the lower and on the upper bound. And now I come to a generalization, sharpening of Khinchin's inequalities, which is due to Yann Bujour and Michel Laurent. They replace the bound 0, in fact, which was standing here on this side, by a term, that is here always negative or 0, or here always positive or 0, so we really have a sharpening. And so far, this was just rephrasing of already known inequalities. But with the help of these new approximation constants, Wolfgang Schmidt and I could establish 2 more inequalities, which go in exactly the same direction, but lead to a result that is really independent of the above estimates. So this means that not one is stronger than the other, nor vice versa, but they are independent. You have to check which one to take in every situation. The interesting thing is that in the case n equals 3, where you have Yannick's identity, with the help of this identity, these two turn out to be equivalent. In all other cases, so n greater than 3, you really have some new information. Okay. Now let's go to section 2, in which I want to explain how a picture of a successive minimum function can give information about simultaneous approximation properties. The philosophy lying behind this is the following. Approximation constants are quite good, but there's more. If you know the dynamical behavior of the functions quite well, if you understand that, you get more information about simultaneous approximation properties as well. So only knowing the constants is not sufficient. We want to know all the functions. first bad news. We will replace the L sub 1 up to L sub n that we got used to now by another n functions, p sub 1 up to p sub n, simply because we do not like the fact that the sum is bounded but not equal to 0. So we try to replace those L sub I by function p sub I in a way that the p and the L do not differ by much. And do not differ by much means we want p sub I of q minus L sub I of q to be bounded by an absolute constant gamma, which depends on n only, as we mentioned. And we want, of course, this is the main goal, we want to have the sum of the p sub I being identical to 0. I do not tell you exactly in which way we define the functions p sub I. It is through standard trick in geometry of numbers. We use compound lattice and pseudo-compound bodies and get some function in this way. But on the one hand, it's technical, and on the other hand, we really do not need this for the talk, because our plan is to isolate some properties that those functions will have, and from these properties, axiomatically, derive how the graph will look like. So it's really not useful to give the exact definition of the p. But having these advantages, we have to take into account that we lose the property that we have like L sub 1 less than L sub 2 less than L sub 3 and so on. We don't have that anymore for the p's, but for j greater than I, we only have the difference bounded by a factor, by a term negative gamma. Also, second drawback is that whereas p sub 1 and p sub n do have...
confusing with the slide. So you say absolute value of pj minus pi is bigger than negative.
Sorry, the absolute value is, we should forget the absolute value, I'm sorry. I'm sorry for that. Yeah. So the difference is greater than minus gamma without absolute value. You're right, there's something really but thanks, at least I noticed that you're paying.
It is true.
It is true, yes. So there's nothing wrong, but I was checking if you pay attention. So whereas p sub 1 and p sub n only have slopes 1 and negative n minus 1, in the way we define them, for the other remaining ones, we have to take into account that slope n plus 1 may occur on very small intervals. Nevertheless, we define n-gamma systems of functions to be systems that satisfy some key properties that are shared by functions stemming from the geometry of numbers, namely from the successive minima functions, and forget about the background from the geometry of numbers and study them as if they were defined axiomatically in that way. Okay, so let's start with an example, namely the special case gamma is equal to 0. In case gamma is equal to 0, we do not make any error. We do only have slopes 1 and negative n minus 1 for all the p's of I. And I'll show you an example of the combined graph of such a system will look like. Okay, so what do we have here? We do have p sub 1, which is this function, p sub 2, which is this one, and so on. And you notice that in any interval, there are exactly 3 functions that are increasing with slope 1, whereas 1 is increasing with slope 3. Of course, there's changes of monotony at points that are indicated below on the q-axis by d and s. The difference between those is the following. At points labeled d, we have this one here, for example. We have a change of monotony of L sub I and L sub I plus 1 with an intersection point of those two, P. And at points labeled S, which are switch points, for example, this one here, we have a change of monotony that does not correspond to an intersection point of two consecutive p's of I. And it doesn't have to be 2 consecutive ones, since we can have a switch point also with L sub 1, p sub 1 and p sub 4 involved. Okay. kind of ideal situation on a certain part of the q-axis. You have to imagine this continues for on and on and on, and the graph may get larger and larger and larger since the functions may tend to minus or plus infinity. But why do we investigate such graphs? Simply because they allow to guess very easily relations between the phi sub I underline or the phi sub I overline, as I've told you. And when you believe this general philosophy that anything that holds true for the special case gamma is equal to 0 is also true for the arbitrary gamma, then you're fine, and you will have proved some new results. So this is a way of guessing new results, but it needs some proof. So we want to get from this ideal situation to so-called real-life conditions. How to do this? Well, the problem is that it becomes difficult when two or more of the p's of I are very close, namely closer than our parameter gamma. Because simply, in this case, we may not distinguish what happens in a strip of width gamma. The solution is, well, don't care about this. Simultaneous approximation properties may be seen by looking at the graph from somewhere far away. So we do not care about the details, we do care about the general behavior. So what we plan to do is we choose an appropriate dissection in intervals, using those division and switch points. We replace the graph of some functions that get very close in the strip by the whole strip of the given width and appropriate slope. We try to glue those strips all together and obtain a cover of our system. In this cover, we have three parameters. Well, we have the dimension, of course. We have the width of the cover, and we have a kind of an error parameter epsilon that I will refer to over the next slide. Because in the next slide, I have prepared some examples to cover, again in the dimension n equals 4, so we have 4 functions. That looks as follows. So when you look at the picture, everything is as before. Just in some parts, we have frequent intersections of 2, or in this case, 3 of the p sub I. This can get messy. We say, okay, we don't care. What we want to know is just the general behavior. So this is this shape is of interest. What we call defining strands in this situation. And when I talk about appropriate slope, the slope is indicated here, depending, of course, on how many of the functions p sub I are involved. The width of the strip is just the difference of the maximum. And finally, the error parameter epsilon that I addressed to a minute ago is a parameter ruling the slope of the ascending parts. So we must, in order to be able to glue together, assure that really two strips meet with the same width, here, 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 and that between two strips, the ascending parts do have a right slope, not too much different from one. And this is where the error parameter epsilon. And the main result of these covers is the following. It says that this procedure really works. And it says that for a given dimension and given error parameter gamma, and for any epsilon greater than 0, there is really such a width, such that you can fit all these functions that come close together in a strip of the given width. And not only for a finite interval, but also for infinite intervals. So the difficulty is to find a width that you may, such that you may glue together all those different strips together to obtain a cover on this interval. And this interval may be infinite. Well, this is not easy. It is done by induction, and the induction is quite complicated, but it has nice consequences. First nice consequence is, well, all the guess results for the case gamma equals to 0 can be proved now, and we get some new estimates, for example, involving the approximation constant, which means some new transfer inequality. And focus in particular for estimates of phi sub 1 underlined in terms of phi sub 1 overlined. So the estimate here looks a little bit messy, but if I rephrase it in terms of omega and omega hat, where omega is what I define as omega 1 and omega hat is what I define as omega hat of 1, then you get this estimate, and if you compare that to Yannick's inequality, which I wrote here, you see that you get an improvement of this inequality for all n strictly greater than 3. Whereas, of course, in the case n equals 3, you get the same as Yannick inequality says. Okay, so we have an estimate for the quotient omega divided by omega hat for all n greater than 3, and better than Yannick's for all n greater equal to 4. This is also the starting point for my last section, which is approximation in dimension 4. So let's come back to the problem that we just dealt with, namely the bound for omega divided by omega half in this case. Professor Moshe had obtained a result that is equivalent to this bound already earlier. And if you compare both bounds, you see that his result is better. So at least in the case n equals 4, the result that we got is not optimal. And of course, we wanted to know, can you guess such a result using the geometric methods I introduced, using the graph that we studied? And the answer is yes, you can. And you can in the following way. The guess is that for the extreme case, and this should be the extreme case if this is a good estimate, that for given phi sub 1 underlined, the value of phi sub 1 overlined is minimal in the case of what we call a regular graph, which is the combined graph of a 4-0 system for which every minimum of L sub 1 corresponds to a maximum of L sub 4 and vice versa. Refer to slide with a picture of a regular graph in this case. So what you see is, first we have a parameter rho intervening, which shows simply how much of the graph is open. So it rules the total angle here. But once rho is fixed, the graph is perfectly determined by the slopes of the ascending parts and the descending parts, and by the fact that any minimum of L sub 1 must be a maximum of L sub 4, and vice versa. So then the graph is really perfectly determined. And what the guess said is that among all graphs of 4 gamma systems, the smallest angle between the approximation constant phi sub 1 underlined and phi sub 1 overlined is as in the regular graph in this case. Now, the regular graph, I can prove that easily, and it turns out that exactly this result comes out, and also by a recent result of Delanois, who gave example of 3 real numbers, psi1, psi2, psi3, for which this bound is obtained. We know that the result is best possible. And also with the same technique, we could get a result in the dual situation, omega star divided by omega hat star. But I did the same estimate recently by with a different approach, as we saw. Here, the linear independence of psi1, psi2, psi3 together with 1 is absolutely crucial, and also you use the fact that for arbitrarily large R and S, the minimal, there is always arbitrarily large R and S, such that the sequence of minimal points contains a sequence of points that span the whole R4, whereas the middle ones, so from X of R to X of S, two-dimensional spaces only span. And the existence of infinitely many such parts in the sequence of minimal points is used to conclude. Remark here, as I noticed in the announcement, Fully will speak about the case n equals 5, and he has together with Moshiri the result where exactly the same kind of estimate of omega in terms of omega hat will be done for the case n equals 5. So they were clever as I was, so they do it one dimension higher, which is good. And here they will give 3 bounds as far as I know for omega divided by omega hat, depending on which linear independence properties of the sequence of minimal points you have. So for example, the easiest case would be, think of a sequence of minimal points where infinitely often you have 5 consecutive ones that are linearly independent. So this is absolutely the dream case, so you get one estimate for this case, and depending on if that happens or not, you distinguish other cases and then you get other estimates. So but you will do that in this. So to conclude my talk, I want to speak about another problem in dimension 4, which I started investigating a couple of weeks ago, namely the approximation of 2 linear. So in this case, we have 4 real numbers, psi1 and psi4, and again a parameter greater than 1. And we use Gauss's theorem to show that there exists an integer point satisfying this system of inequalities. Now we don't have 3 inequalities for simultaneous approximation, but we have rather 2 linear forms that are approximate, with z1 and z2 undefined. So the procedure is the same. We again consider an appropriate lattice and appropriate convex bodies, depending on our parameter q, to define minimum functions, and also the related approximation constants, phi sub y, underlined and overlined. So same procedure as in the other problem. And the guess would be the same, namely that the extremal case, for which phi sub 1 underline is given, and the phi sub I overline is minimal, then if we're in the case of a regular graph corresponding to this problem. So what is it? Well, then it looks this way. Again, we have the parameter rho ruling the total angle here. After this, everything is determined by now knowing that all the slopes of the increasing parts is 1 and the decreasing parts -1. We have a problem that is self-dual in this case. So the graph is symmetric with respect to reflection on the q-axis, and this q-axis again is by duality the line of slope phi 2 overline or phi 3 underline, which is 0 in this case, and this angle is the one between phi sub 1 lower and upper part. This is the thing that we investigate. And yeah, as before, of course, it's a regular graph, so any minimum of L sub 1 corresponds to a maximum of L sub 4. So what about here? Of course, we first need to define the suitable approximation constant omega and omega hat in this case, and of course check what is the relation between the phi sub I underline and underline. Good, so in this case it's not that complicated. You get simple relations between omega and phi sub 1 underline and omega hat and phi sub 1 overline. Yeah, and it just remains now to check what comes out if we do the same, play the same game again. We get an estimate. Now I have written it in terms of omega greater than some function of omega hat. You could divide by omega hat again to get something in the same flavor as before. That, I think, is it. Thank you.
Questions, remarks?
Please. So you conjecture that for any picture or graphs satisfying your abstract constraints, there's actually a lattice or a vector of real numbers for which this is up to some finite error. This is the same.
This is not only a good question, this is an excellent question, but also a very hard question, I think. Because the problem is, how can you say to any picture corresponds something? When are two pictures the same? I mean, if I change something in the beginning, I get two different pictures, but for simultaneous approximation, it does not matter at all. I mean, this is just the, I use the notion, look to it from far apart, far away. So if it has the same structure, if it has the same flavor, but how to define that? That is the main problem in this question. But once this definition is given, I think the answer is yes.
So I mean, the easier question would be, if given the values of omega I, upper line, underline, find the lattice with those particular values of that number?
In some cases, for example, Bujold and Laurent did it in the case n equal 3. So for any given value of the approximation constants, they didn't do it with phi, but for omega and omega hat and omega star and star. Then you get really there exist lattice, respectively real numbers, xi1, xi2, xi3, for which these approximation constants, for which these numbers are the approximation constants. But it is not known in general. But in the case n equal 3, it's done. And we think that these graphs may lead to a proof for n greater than 4, but really the problem is that you have to write it down somehow, get a definition of what you mean by looks like.
More questions? And dimension 4 is the last dimension. Because I think that today is 2014 here.
Yes.
Four. And you have 4 variables.
Yes, but carefully speaking about n equals 5, so there is already progress. So for 2015, it should be good.
Thank you very much. More questions? Thank you. Again?